Hi, welcome to Inside Out Math. This video is a lesson on iterated integrals, and today we'll just be deriving the definition of iterated integrals. What you'll need to know going into this lesson really is single variable integration, including your integration techniques. Knowing that you've gone this far in the calculus series, you're probably okay with that. And again, we'll be going through the derivation of iterated integrals as well as Fubini's theorem. As we go through the derivation, I'll try to do a geometric interpretation side by side, as well as the notation. And let's just recall that it's usually difficult to evaluate single integrals directly just from the definition of an integral. What we're interested in now is volume. Single integration gives us area. Now double integration, which is pretty much single variable integration twice, will give us volume. Now, again, double integrals, just from your first principles, is pretty difficult as well when you have to do midpoint rule, left-hand endpoints, right-hand endpoints, all that stuff. But we'll see in this derivation how to express a double integral as an iterated integral. And as we go through the derivation, I'll try to do a geometric interpretation side by side with the notation. So let's just go ahead and scroll down here. And now let's just start with the notation. So let's go ahead and take a single variable integral from c to d of a multivariable function, say f of x, y, with respect to y. Now what does this mean here? Take an integral of a function of variables x and y with respect to y. It means we'll hold x as constant, the variable x as constant to this function, and integrate with respect to y from the bounds c to d. Now what this is called is partial integration. Partial integration with respect to y. Okay, notice the correlation between partial integration and partial differentiation. We hold one of the variables, or all of the variables except for the independent variable. We hold those constant and differentiate or integrate with respect to the independent variable. Since this integral is a number that depends entirely on the value of x, it defines a function of x, and I'll call it some area function of x. We'll start by drawing some surface and a set of axes. And we'll project the surface onto the xy plane and call it our domain. Not exactly the parallelogram that I want, but that's fine. Now what we have, again, is area. So I'm going to draw some cross-sectional area perpendicular to the x-axis from value c to d. Oh, and you'll hear my sister there. And the surface here is described from c to d along the y, from say c to d. And as you can see, I've drawn some cross-sectional area. I'll call a of x. Now going back to notation here, now what if I integrate with respect to x on the left-hand side of this equation? If I do that on the left-hand side, I must do it on the right-hand side. So I need to do it with respect to x since we have a function of x here. And so I'll have to do it on this right-hand side, and I'll bracket off this part from c to d of f of xy, dy, and finally dx. And omitting the brackets, and double integral from a to b and c to d of f of xy, dy, dx. And this here is the definition of an iterated integral. We'll go ahead and switch back to what this means in geometry. Well, this area here, we'll go ahead and stack up a bunch of areas from bounds a to b, and we'll say from a to b here. Take all these areas, and what do you get when you stack up all those areas? Well, we'll get some volume inside this surface. Now computationally, we'll start with the inside integral. We'll call it the inside integral. Partial integrate with respect to y. We'll do the inside integral, and you get out some number. And then integrate with respect to x. If this is your first time dealing with iterated integrals, it should make much more sense as you do more examples. And as promised, we'll talk about Fubini's theorem. We won't prove it, but we'll look at the geometric description. So Fubini's theorem is as follows. Let f of x, y be continuous over a region R, when I say R for rectangle, where R is a set of x, y such that x ranges from A to B and y ranges from C to D. So what we're looking at here is in fact a rectangle if A and B, C and D are real numbers. Then the double integral over the region R of f of x, y, dx, dy, this should be actually dA, I should say, equals the double integral from C to D, A to B of f of x, y, dx, dy. And this also equals the double integral from A to B, C to D of f of x, y, dy, dx. Now, if you can tell the difference between these two integrals here, all we're switching is the bounds. And if we switch the bounds, then we switch our differentials. Now, what I want to talk about is why this works. Now, if you look back, you could easily start off with a cross-sectional area along the perpendicular to the y-axis, I should say, and that would mean maybe a cross-sectional area equals the integral from a to b of some function f of x, y, dx. Now, what does this mean geometrically? Well, we'll take some cross-sectional area, boom, 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 okay, perpendicular to the x, or to the y-axis, I should say, and it ranges from A to B. Integrate the left-hand side with respect to it would be to y, from C to D of dy. So I must integrate with respect to y on the outside of this single variable integral from C to D, dx, dy. And we would be integrating this cross-sectional area from C to D, meaning we'll get the same volume of the surface. Up next will be a few examples. Thank you for watching.